The code defines a function called make-LSTM that creates a recurrent neural network (RNN) model called LSTM. This model uses inputs of shape 241 and creates a layer of CUDNN LSTM with 25 units and return sequences set to false. This layer is then followed by a dropout layer with a rate of 0.1 to prevent overfitting. The output of the dropout layer is then passed to a dense layer with 2 units and softmax activation. The model is compiled using categorical cross-entropy as the loss function, RMS prop as the optimizer, and accuracy as the metric. Finally, the model summary is printed and the model is returned. Overall, this code creates an RNN model using LSTM with specific layers and parameters, compiles it with appropriate settings, and returns the model for further use. The callback's rec function takes a parameter model type and sets it to LSTM by default if no value is provided. A CSV logger is created using the CSV logger method, which will log the training progress of the model in a CSV file. The file name is based on the model type and the test year. A file path is created using the model folder variable, which will store the trained model in a specified directory with a unique name based on the model type, test year, and epochs. A model checkpoint is created using the model checkpoint method, which will save the model to the specified file path at the end of each epoch. An early stopping function is also created using the early stopping method, which will monitor the validation loss and stop training if no improvement is seen after 10 epochs, while also restoring the best weights of the model. The function then returns a list containing the CSV logger, early stopping function, and model checkpoint to be used in the training process. This code takes in an input array and performs several operations on it before returning a reshaped array. First, the input array is split into 3 subarrays along the second axis. Then, the order of the subarrays is rearranged so that the first and second axes are swapped. Finally, the second and third axes are also swapped. This results in a reshaped array with a different order of the dimensions compared to the original array. This code is using NumPy functions to manipulate the array, as indicated by NumPy notation before each function. This code does not make any changes to the original array, but rather creates and returns the reshaped array. This code trains a model using a specific model type, default is LSTM, and training and test data. First, the training data is randomly shuffled. Then the input features, target variable, and return are extracted from the training data and reshaped appropriately. The target variable is also transformed using one-hot encoding. For LSTM models, a specific LSTM model is created, otherwise the program returns. Next, callbacks are specified based on the model type. Then, the model is trained using the training data with a validation split of 0.2 and 1000 epochs. After training, the code creates a list of unique dates in the test data. For each date, the code gets the test data for that date, reshapes it, and uses the trained model to make predictions for that date. Finally, the trained model and the predictions for each date are returned. This code is a function that takes in 3 parameters: file name, train data, and test data. It first loads a pre-trained model using the file name parameter. Next, it creates a list of unique dates from the test data and stores it in the variable dates. Then, it creates an empty dictionary called predictions. The code then iterates through each date in the dates list and filters the test data to only include data for that particular date. This filtered data is then reshaped and used to make predictions using the pre-trained model. The predictions for each date are stored in the predictions dictionary with the date as the key. Finally, the function returns both the pre-trained model and the predictions dictionary. This code starts by defining a function named simulate that takes in 2 arguments, test data and predictions. It creates a new data frame named rets with 2 columns named long and short. The value of rets is empty for now. Next, the code sets the value of k to 10, which will be used later on in the code. Then it loops through the keys of the predictions dictionary in sorted order and assigns each key to the variable day. Inside this loop, the code first assigns the value of predictions day to the variable preds. It then uses this value to filter the test data by selecting the rows where the first column matches the value of day. This filtered data is then assigned to the variable test returns. Next, the code sorts the predictions day array and selects the top k indices, which are then reversed. These indices are assigned to the variable top preds. Similarly, the code also sorts the predictions day array and selects the bottom k indices, which are then reversed. These indices are assigned to the variable worst preds. To calculate the returns for long positions, the code takes the test returns at the indices specified by top preds and assigns the result to trans long. Similarly, to calculate the returns for short positions, the code takes the negative of the test returns at the indices specified by worst preds and assigns the result to trans short. The code then updates the rets data frame by adding a new row with the mean of trans long and trans short as its values, with the index being the value of day. After the loop is completed, the code prints the mean of rets and returns the rets data frame. This function essentially simulates a stock trading strategy using the given test data and predictions and returns the average returns for long and short positions. This code creates a label for a data frame by dividing the closing price of each stock in the data frame by the opening price and then calculating the percentage change. It first checks if the date indexes for the closing and opening prices match, and if not, it prints an error message. It then calculates the cumulative sum of the given percentages, defaulting to 50% each, and assigns them to the label. This label is then used to rank and group the percentage changes, with the resulting categories being assigned as labels. These labels are then returned for use in the data frame. This code is a function that creates a stock dataset for a given stock. It takes in two data frames, one for opening prices of the stock and one for closing prices, along with the stock name and a default value of 240 for a parameter. It first creates an empty data frame called stdata and adds two columns, date and name, with the date values from the closing price data frame and the stock name in every row. It then calculates the daily change for the stock by dividing the closing price by the opening price and subtracting 1. This is done for a range of m days, which is reversed using the reverse function. The result is then added to the data frame as intra-R columns for each day. Next, an intra-R future column is added by shifting the daily change 1 day forward. A label column is created and filled with the corresponding label for the stock from a label list. The last two columns, month and trade year, are added by first extracting the month and year from the date column and then dropping the month column. The resulting data frame is then filtered by the trade year for the test year. The function finally returns two arrays, one with the training data and one with the test data for the stock. This code uses the function scalar normalize to normalize the data in both the train data and test data arrays. It begins by using the robust scalar function to create a scalar object. Then, it uses the fit method to calculate the appropriate scaling values for the data in the train data array, specifically the values in columns 2 through -2. These values are then applied to the same columns in the train data array using the transform method. The same process is then repeated for the test data array, using the same scaling values calculated from the train data. This ensures that both the train and test data are normalized using the same scaling values. Overall, this code helps to standardize the data and ensure that it is in a consistent format for further analysis or modeling. This code takes in two sets of data, train data and test data, as inputs to train a model. First, it sets a random seed for the random module and the NumPy module, ensuring that the random values generated during training and testing will remain consistent for each execution of the code. Next, the code creates two variables, train X and train Y, by selecting certain columns from the train data input. The train X variable contains all the columns of train data except for the first two and the last two columns. The train Y variable contains the last column of train data. The code then converts the values in train Y to integers. After printing a message to indicate that training has begun, the code initializes a random forest classifier model with specific parameters, such as n estimators, max depth, and random state, to be used for training the model. The model is then fitted using the train X and train Y values. A second message is printed to indicate that training has been completed, along with the model's accuracy score on the training data. The next section of the code creates a list of unique dates from the first column of test data and initializes an empty dictionary for predictions. It then loops through each date in the dates list and selects all the rows in test data that have that date on the first column. The corresponding rows are then removed from the original test data and stored in a variable called testD. The first two and last two columns of testD are then selected and assigned back to testD. Next, the code uses the trained model, CLF, to predict the probability of the testD values belonging to class 1. These predicted probabilities are then stored in the predictions dictionary, with the corresponding date as the key. Finally, the code returns the predictions dictionary as the output of the function. This code starts by defining a function called simulate, which takes in two parameters, test data and predictions. The function then creates an empty data frame called rets and initializes it with two columns, long and short. In the next line, the variable k is set to 10, which will be used later in the code. The code then enters a for loop, which iterates through each key in the dictionary predictions. Inside the for loop, the code first retrieves the values associated with the key day in the predictions dictionary and stores them in a variable called preds. Next, the code uses the day key to filter out the relevant rows in the test data frame and stores them in a variable called test returns. The next two lines use the argsort function to sort the predictions from highest to lowest and lowest to highest, and then select the top and bottom k values, which were defined earlier in the code. These values are then used as indices to retrieve the corresponding values from the test returns variable. These values are stored in two separate variables, trans-long and trans-short. The final line inside the for loop uses the lock function to insert a new row in the rets data frame, with the day as the index and the mean of the trans-long and trans-short values as the values for the long and short columns, respectively. After the for loop ends, the function returns the rets data frame, which contains the daily average of the trans-long and trans-short values for each day in the predictions. This code takes in two data frames, df_open and df_close, as well as a list of percentages. It first checks if the date indices of the two data frames match, and if not, it prints an error message and returns. The percentage list is then modified to include 0.0 at the beginning and the cumulative sum of the original percentages. A new data frame, called label, is created by applying a lambda function to the ratio of values from df_open and df_close, which calculates the ranking of each row and then assigns it to a specific quantile based on the percentage list. This quantile is then used as the label for the data frame. Finally, this labeled data frame is returned. Essentially, this code is creating labels for the data based on the ranking of values from df_open and df_close and the specified percentages. This code is a function that takes three parameters, df_close, df_open, and st. It creates an empty data frame and adds two columns to it, date and name, which contain the same values as the date column in df_close and st. It then calculates the daily change by taking the ratio of the close price and open price from df_close and subtracting 1. The code then creates a list of numbers from 1 to 20 and from 20 to 241 in increments of 20. For each number in the list, it adds a new column to the data frame called intra_r, followed by the number. This column contains the ratio of the close price from the previous day to the open price from the current day, subtracted by 1. The code also adds the daily change, labels, and month to the data frame. It then removes any rows with missing values and creates separate data frames for the training and testing data based on the year in the month column. Finally, it returns the training and testing data as NumPy arrays. The purpose of this code is most likely to create a dataset for machine learning or statistical analysis, with columns representing different factors that could potentially affect stock prices. This code creates a LSTM, long short-term memory neural network model using Keras library in Python. The make LSTM function is defined and it takes in no arguments. Inside the function, an input layer with shape 243 is created using the input function from keras.layers module. This indicates that the model will take in input sequences of 240 time steps with 3 features each. Next, a QDN LSTM layer is added to the model with 25 units neurons. This layer is a faster and more optimized version of the traditional LSTM layer. The return sequences parameter is set to false, which means that the output of the LSTM layer will be a single vector rather than a sequence. This layer is followed by a dropout layer, which randomly drops 10% of the neurons to prevent overfitting. Finally, an output layer with 2 neurons is added to the model. This layer uses a softmax activation function which converts the input into probabilities, making it suitable for multi-class classification. The model is then compiled using categorical cross-entropy as the loss function, RMSProp as the optimizer, and accuracy as the metric to monitor. The model.summary function is used to display a summary of the model architecture. The model is then returned to be used for training or inference. This function, callbacksRec, takes in a parameter called model type and sets the default value to be LSTM if no value is provided when the function is called. First, it creates a CSV logger object, which logs the training process for the model by saving the results in a CSV file named training_log.dat plus model type mash plus start test year plus CSV. Then it creates a file path for saving the model's weights as the training progresses. The file name includes the model type and the test year. Next, it creates a model checkpoint object, which saves the model's weights after each epoch if the validation loss is improved. Finally, it creates an early stopping object, which stops the training process if the validation loss does not improve for 10 consecutive epochs, and restores the weights of the best performing model. The function then returns a list containing the CSV logger, early stopping, and model checkpoint objects for later use in the code. This function reshapes an array of elements into a new array. The input array is first split into 3 equal parts along the horizontal axis, resulting in a new array with 3 columns. Then, the columns and rows are swapped to change the shape of the array. Finally, the resulting array is returned. First, the function trainer is defined with two parameters, train data and test data, which represent the training and testing datasets respectively. Then, the np.randombot_shuffle function is used to shuffle the training data in order to avoid any bias in the data. Next, the training data is split into three arrays using slicing. Train X is created by selecting all rows and columns 2 to the second last column. Train Y is created by selecting all rows in the last column, and train ret is created by selecting all rows and the second last column. Next, the reshaper function is used to reshape the train X array. Then, the train Y and train ret arrays are reshaped using the np.reshape function with a -1 dimension. The one-hot encoder function is used to convert the categorical values in train Y into numerical values. Then the ny array is created by transforming the train Y array into an array of arrays. The train ret array is then horizontally stacked with a column of zeros using the np.hstack function. Next, the make LSTM function is used to create a LSTM model, and the callbacks rec function is used to define the necessary callbacks for training the model. The model.fit function is then used to train the LSTM model with the training data, setting the number of epochs to 1000, a validation split of 0.2, and a batch size of 512. The set function is used to create a list of unique dates from the first column of the test data array, and a for loop is used to iterate through each date. Within the loop, the reshaper function is used to reshape the test data array for each specific date. Then, the predict function is used to make predictions for the reshaped test data array, and the probabilities for the second column are stored in the predictions dictionary with the date as the key. Finally, the trained model and the predictions dictionary are returned by the trainer function. This function takes in three parameters: file name, which is the name of a file, train data, which is a set of training data, and test data, which is a set of data used for testing. It loads a pre-trained model from the file and stores it in the model variable. It then creates a list of unique dates in the test data and stores it in the dates variable. Next, it creates an empty dictionary called predictions. Using a for loop, it iterates through each date in the dates list and selects only the rows from the test data that have the same date as the current iteration. It then reshapes the selected data to be in the format expected by the model. The model makes a prediction based on this data and stores it in the predictions dictionary, with the date as the key and the prediction as the corresponding value. Once all the dates have been iterated through, the function returns the model and the predictions as a tuple. The code first defines a function called simulate with two parameters, test data and predictions. It then creates an empty data frame called rets with two columns, long and short. Next, it sets a variable k equal to 10. Then, it starts a loop over all the keys in the predictions dictionary, using the sorted function to ensure they are in order. Within the loop, it first sets the variable preds equal to the values associated with the current key in the predictions dictionary. Next, it uses the current key to filter the test data array and only keep rows with a first column equal to the current key, getting the test returns from the last column. It then sorts the preds array in descending order and selects the top k values, storing them in the top preds array. It also sorts the preds array in ascending order and selects the top k values, but this time it reverses the order using the 1 notation and stores them in the worst preds array. Next, it calculates the mean of the test returns for the values in top preds and assigns it to the trans_long variable. It then multiplies the values in test returs corresponding to the values in worst preds by -1 and calculates their mean, assigning it to the trans_short variable. Then it adds a new row to the rets data frame with the current key as the index and the values in trans_long and trans_short as the values for the long and short columns respectively. After the loop is complete, it prints the mean of the rets data frame and returns the data frame as the output of the function. The code first takes in two data frames, one for opening values and one for closing values, along with an optional list of percentages. It then checks if the date indexes of the two data frames match, and if not, it prints an error message and exits the function. Next, the list of percentages is converted into a cumulative sum and added to a list that includes 0. This list is then used to calculate the labels for each row in the data frames. This is done by dividing the closing values by the opening values and subtracting 1. Then, using the lambda function, the values are ranked and split into bins based on the percentages. Finally, the labels are returned, excluding the first row. This code is likely used to categorize the performance of different stocks or assets within a dataset. This code takes in two data frames, df_open and df_close, and a stock name, st, and then creates a new data frame called stdata. The new data frame includes columns for the date, stock name, and daily change in stock price. It also creates columns for daily changes in stock prices for the past 240 days. Next, it calculates the next day's return for the stock and adds it as a column to the data frame. Then, it calculates the change in closing stock price and adds it as a column for the past 240 days. It also adds a column for the future intraday return and labels for each row. The data frame is then filtered based on the year and divided into training and testing data. Finally, the training and testing data are returned as NumPy arrays. This code first defines a function called scalar normalize that takes in two arguments, train data and test data. Inside the function, a scalar object from the robust scalar class is created. This scalar is then fitted to the data and train data, specifically the columns starting from the third column to the second to last column. This means that the scalar will use the data in these columns to determine how to transform the data. Next, the code applies the scalar's transformation to the same columns in train data and also to test data. This means that the data in these columns in both train data and test data will be normalized using the same scaling values determined by the scalar object. Essentially, this code implements a normalization technique called robust scaling on specific columns in the train and test datasets. The code takes in two sets of data, namely the training data and test data. It then sets the random seed to a specific value for reproducibility and uses this value to seed both the random and NumPy libraries. Next, it extracts the input features, train X, and the target labels, train Y, from the training data. The target labels are then converted to integer values. After this, it prints a message to indicate that training has started. The code then creates a random forest classifier using the random forest classifier function from the scikit-learn library. This classifier is trained using the training features, train X, and labels, train Y. The classification accuracy of the model is then printed. Next, the code creates a list of unique dates present in the test data. It then iterates through each date and filters out the data for that specific date. This filtered data is then passed through the trained model to make predictions, and these predictions are stored in a dictionary with the date as the key and the predicted probabilities as the values. The final output of the code is a dictionary containing the predicted probabilities for each day in the test data. This dictionary is then returned as the output of the trainer function. The first line defines a function named simulate that takes in two arguments, test data and predictions. The second line creates a new data frame named rets, which has two columns named long and short. The third line initializes a variable k with the value of 10. The fourth line begins a for loop that iterates over the sorted keys of the predictions dictionary. Inside the for loop, the fifth line assigns the value of the current key to the variable day. The sixth line accesses the predictions dictionary using the current day as the key and assigns the value to the variable preds. The seventh line uses Boolean indexing to filter the test data array to only include rows where the first column is equal to the current day, and then selects the second to last column. This filtered array is assigned to the variable test returns. The eighth line uses the argsort function to sort the predictions for the current day and returns the indices of the sorted array. These indices are then reversed and the last k values are selected. These indices are assigned to the variable top preds. The ninth line calculates the returns for the long positions by using the indices of the top predictions and selecting the corresponding returns from the test returns array. These returns are assigned to the variable translong. The 10th line does the same as line 9, but for the worst predictions. The returns are multiplied by -1 to represent a short position and are assigned to the variable transshort. The 11th line inserts a new row into the rets data frame with the values of the mean of the translong and transshort arrays for the current day. The 12th line returns the rets data frame as the output of the simulate function. This code starts by defining a function called createLabel that takes in three arguments, dfopen, dfclose, and perk. The first two arguments refer to data frames containing information on opening and closing stocks, and the third argument is a list of percentages. The first line in the function ensures that the date index for both data frames are the same. If they are not, the function will return an error message. Next, the code creates a list that starts with 0 and increments by the percentages given in the argument perk. This list will be used later in the function. Using the closing and opening data frames, the code then calculates the difference between the values and converts it into a percentage change. This calculation is applied to all columns except for the first one. Finally, the code computes the rank of each percentage change using the qcut function and assigns a label based on the percentages given in the argument perk. This label is then returned as the output of the function. This code creates a stock data frame with information from the input data frames dfclose and dfopen for the given stock ST. The created data frame contains columns for the date, stock name, intraday returns, daily closing returns, overnight returns, future returns, label, and month. The code then creates a training and test dataset and returns them in the form of arrays for use in a machine learning model. In simplest terms, this code creates a simple LSTM model with the desired number of cells, default of 25. Inputs are defined as a sequence of length 1, and an LSTM layer is added with the specified number of cells, using a hyperbolic tangent activation function and a sigmoid recurrent activation function. Dropout and recurrent dropout are also applied to prevent overfitting. The output is a dense layer with 2 nodes and a softmax activation function. The model is compiled with the categorical cross-entropy loss function and the RMS prop optimizer, and accuracy is used as a metric. Finally, a summary of the model is printed and the model is returned as the final output of the function. This code can be used to create a simple LSTM model for various tasks, such as classification or prediction. This code defines a function called make_tudnn_LSTM with an input parameter of cells that defaults to 25. The function takes in an input shape of sequence length 1 and assigns it to the variable inputs. Then, the function uses a QDNN-LSTM layer with the specified number of cells to process the input data. A dropout layer with a 0.1 rate is applied to the output of the QDNN-LSTM layer. The final output layer has a softmax activation function and 2 units. The function then compiles the model using a categorical cross-entropy loss function, RMS prop optimizer, and accuracy as the metric. Finally, it outputs a summary of the model and returns the compiled model. This code defines a function called callbacksRec that takes in a parameter called model type, which has a default value of LSTM. The function starts by creating a CSV logger, which will log the training progress of the model and save it to a CSV file. The CSV file is named by combining the model type, test year, and extension.csv. Then, it creates a file path for saving the model, which includes the model type, test year, epoch, and extension.h5. Next, it creates a model checkpoint, which will save the model only when there is an improvement in validation loss. Finally, it creates an early stopping callback, which will monitor the validation loss and stop the training process if there is no improvement after a certain number of epochs, specified by the patience parameter. The function then returns a list containing the CSV logger, early stopping callback, and model checkpoint callbacks. This code is a function that trains a model and then uses it to make predictions on a test dataset. The function takes in 3 inputs, the training and test datasets, and the type of model to be used. The first line shuffles the training data randomly. The next 4 lines extract the features and labels from the training data and reshape them into the required format for the model. Then, an encoder is used to convert the labels into one-hot encoded vectors. The if-else statement checks the type of model requested and calls the appropriate function to create it. Once the model is created, necessary callbacks are set up. The model is then trained on the training data for a specified number of epochs using a batch size of 512. A validation split of 0.2 is used to evaluate the model on a subset of the training data. Next, a list of unique dates in the test dataset is created, and a dictionary is initialized to store the predictions for each date. A for loop goes through each date and extracts the features for that particular day from the test dataset. These features are then reshaped and used to make predictions using the trained model. Finally, the predictions for each date are saved in the dictionary and returned as the output of the function. This code is a function that takes in 3 parameters, a file name, training data, and test data. The first step is to load a pre-trained model using the file name provided. Then, the code creates a list of unique dates from the test data. Next, it creates an empty dictionary called predictions. The code then iterates through each date in the list of dates. For each date, it selects the rows of the test data that correspond to that date and reshapes the data into a format that the model can use for prediction. The predictions for that specific date are then stored in the dictionary. Once all the dates have been iterated through, the function returns the dictionary of predictions for each date. The first line of code defines a function named simulate that takes in 2 parameters, test data and predictions. The function returns a data frame with 2 columns, long and short. Next, a new data frame named rets is created with 2 empty columns, long and short. The variable k is assigned a value of 10. A for loop is then set up to iterate through each day in the sorted list of keys in the predictions dictionary. Inside the loop, the variable preds is assigned to the predictions for the current day. Next, the variable test returns is assigned to the test data for the current day by selecting rows where the first column matches the current day and selecting the second to last column. The top predictions for the current day are then selected by sorting the predictions for the day and selecting the top k values. The variable trans_long is assigned to the test returns for the top predictions. The worst predictions for the current day are then selected by sorting the predictions for the day and selecting the bottom k values. The variable trans_short is assigned to the negative of the test returns for the worst predictions. The values for the current day are then added to the rets data frame in a new row with the values for long and short, calculated by taking the average of the trans_long and trans_short values. Finally, the rets data frame is returned by the function. This code creates a label for a given data frame using a specified percentage split. The first step is to define the percentage split, which is initially set to 0.5, 0.5, meaning the data frame will be divided into two equal parts. Then, the code uses the NumPy cumulative sum function to add the starting value of 0.0 to the percentages, creating a list of cumulative percentages. Next, the code selects all rows and columns except the first column, which is usually used for time series data, from the data frame, and then applies the PCT change function to calculate the percentage change between each row and the row above it. This is used to standardize the data and avoid bias in the classification. The fill method parameter is set to none, meaning it will not replace any missing values with a specified method. The 1 indexing is used to start the percentage change calculation from the second row, as the first row will always have a NaN value. Then, the code uses the apply function to divide each row into different categories using the qcut function, which splits the data into equal-sized bins based on the rank of each value. Finally, the axis parameter is set to 1, which means the qcut function will be applied along the rows. The resulting label is then returned. The first line of code creates a function named createScore_stock_data with two inputs df and st. The next line calculates the daily change of the stock by dividing the stock price by the previous day's price. The third line creates an empty data frame named stData. The next two lines add columns date and name to the data frame and assigns the value of st to the name column. The following lines use a for loop to iterate through a range of 240 values in reverse order. Inside the loop, the data frame is updated with a new column named r, followed by the current index value from the loop, which is converted to a string. This column contains the daily change of the stock shifted by the index value, essentially creating a column for each day in the past. Two columns, r_future and label, are also added to the data frame, with label containing stock information for a particular label, and r_future containing the stock change for the following day. Once the loop is completed, the next two lines assign values to the label column using a list of stock information for the st input and a NumPy library function to add a NaN value. The last three lines add another column month to the data frame, containing the month information extracted from the date column of the input data frame, and drops any rows with missing values. Next, the year is extracted from the month column and stored in a new column named trade year. The data frame is then updated to drop the month column. The next two lines create two new data frames, stTrain data and stTest data, by filtering out rows with trade year values less than the test year input and equal to the test year input, respectively. Finally, the function returns a tuple of two NumPy arrays, one containing the training data and the other containing the test data. The code first defines a function called normalize that takes in three arguments: train data, test data, and norm type. The default value for norm type is set to standard scalar. Inside the function, the code creates a scalar object depending on the value of norm type. If norm type is standard scalar, the scalar object created is of type standard scalar. If it is any other value, the scalar object is of type robust scalar. Next, the scalar object is fitted using train data, which essentially computes and stores the mean and standard deviation of the data. This information will be used later for scaling the data. Then the third and fourth columns, index 2 to nidus 2 of train data, are scaled using the transform method of the scalar object. This is done by subtracting the mean and dividing by the standard deviation. The same scaling is then applied to the corresponding columns in test data. This ensures that both train data and test data are scaled in the same way, using the same mean and standard deviation values from the train data. Overall, this code normalizes the data by scaling it using either standard scalar or robust scalar based on the norm type specified, and then applies the same scaling to both the train data and test data. This helps in making the data more standardized and can improve the performance of certain algorithms. This code first defines a trainer function with two parameters, train data and test data. The function then sets a random seed and uses it to generate random numbers for reproducibility. It then converts the train y column to an integer type, prints a message indicating that the training process has started, and creates a random forest classifier model with specified parameters. The function then trains the model using the training data and prints the model's accuracy score. Next, it creates a list of unique dates in the test data and creates an empty dictionary to store the predictions. It then loops through each date and selects the rows in the test data with that date. These rows are then used as the test set for the model, and the predicted probabilities for each row are stored in the dictionary. Finally, the function returns the dictionary of predictions. This code takes in two arguments, test data and predictions, and creates an empty data frame called rets with two columns named long and short. Then it sets k equal to 10. Next, a for loop is used to iterate through the sorted keys of the predictions dictionary. Within the loop, the code retrieves the predictions for the current day from the predictions dictionary. It then filters the test data based on the current day and selects the second to last column, representing the test returns for that day. The next line finds the top k predictions for that day by using the argsort function, which sorts the predictions in ascending order and returns the indices of the sorted values. Then the matter k notation is used to get the last k values, and the nova1 notation is used to reverse the order, giving us the top k predictions in descending order. These indices are used to retrieve the corresponding test returns for those predictions and assign them to the variable translong. A similar process is repeated to find the worst k predictions for the day using the same argsort and indexing techniques, but this time the order is not reversed. The corresponding test returns for these predictions are multiplied by my -1 and assigned to the variable transshort. Finally, the daily returns are calculated by taking the mean of the top and worst predictions and storing them in the rets data frame for the current day. The loop continues until all days in the sorted keys have been processed. Once the loop is complete, the rets data frame is returned, containing the average returns for the top and worst predictions on each day. The code first takes in a data frame as input, along with a list of percentages. Default is 0.5 for each. Next, the list of percentages is modified to include as 0.0 at the beginning, and then calculates the cumulative sum using NumPy. Then, the code takes the data frame and selects all columns except the first one, index 1 onwards. The percentage change is then calculated for each row. This is followed by applying the lambda function to each row, which ranks the values in each row using the first method, and then divides the values into bins based on the list of percentages created earlier. The resulting indices from the binning process are then returned as the label for each row. Overall, this code is used for creating a label for a financial data set based on the percentage change in values and binning them into different categories. This code creates stock data by taking in a data frame and the stock's name as parameters. It then creates an empty data frame called stData and adds two columns, one for the date and one for the stock's name. It then loops through a list of numbers and adds columns to see data for each number, representing the percent change in the stock's price over a certain time frame, either 1 day or 20 days. It also adds a column for the percent change in the stock's price over the next day. It then adds a label column and a month column based on the date column. It drops any rows with missing data and creates a train data and test data dataset based on the year of the data. Finally, it returns the train and test data for the stock as NumPy arrays. This code defines a class called statistics and initializes it with a series of data as an input. Then it calculates the mean, standard deviation, standard error, percentage of positive values, skewness, kurtosis, value at risk, conditional value at risk, maximum drawdown, and Sharpe ratio for the given data. Lastly, it provides functions to display a short report and a detailed report of the calculated statistics. It utilizes various libraries such as NumPy, Pandas, and SciPy.stats to perform the necessary calculations.